We talked in the past about how all physical phenomena, light, matter, gravitational fields, how all of these things seem to be waves in a medium, waves in an ether. But how can we implement that perspective mathematically in a way that develops a theory that identifies the specific nature of that ether? Today, we'll be interviewing Dennis Braun. Dennis is an independent researcher who's working in Germany alongside a number of other physics professors, and he is going to tell us today his group's work on solitons, which are particular kinds of oscillations which have been observed in media such as water and plasma. And we have found that these particular kinds of waves interact with one another much in the same way that particles do. And so these solitons are a natural candidate for the true nature of the ether and how each part of it interacts with the other. So let's delve deeply into this promising hypothesis of how the ether really works here on Inductica. Dennis, I'm really thrilled to have you on Inductica today. I was really impressed by your speech at the PAMO conference. For those of you who are new to all of this, the PAMO conference was a conference, a physics conference given in Munich, Germany by the Dialect organization and by Independent Physics. And it was a meeting of a lot of people who are not satisfied with the current approach to physics. We weren't satisfied with the lack of physical explanations, the fact that much of modern physics is a bunch of floating math that does not identify physical cause and effect relationships. And so all of us gave presentations on our understanding of what might be going on for real in these physical phenomenon, and something that was unexpected. We knew that we would agree to some level on philosophy, but what we were really surprised about is the degree to which we ended up agreeing on the specifics of what's physically happening. And your presentation really stood out to me, so I wanted to bring you on so that you could tell my audience about your ideas. Well, they're not just your ideas, but you're working with a number of other people who I'm sure you're going to mention about solitons. So take it away, Dennis.
Yeah, thank you, James, for inviting me. And I also really enjoyed the PAMO conference, and it was not just about throwing math at each other's head, but digging what's going on in physics. And maybe I just start with giving a little overview of how one gets to the soliton idea, that particles are solitons, and what, to my opinion, amazing conclusions one can draw from that, and how much one could possibly explain, which is today unexplained. And yes, you already told about the Machian ideas and the idea of unification and gravity, and of gravity and inertia. Yes, if one follows these ideas, one can derive the inertial mass from the gravitational one. So one sees that inertial mass is actually not a fundamental property of particles, but it is a derived property. And there's much evidence for this approach. One is surely the equivalence principle. And yes, if the inertial mass doesn't remain as a fundamental property, but only the gravitational mass, one can draw some interesting conclusions from that. Namely that if one thinks about it, that gravitational mass only has a meaning with respect to the gravitational field. And on the other side, there is no gravitational field without gravitational mass. And this some kind of suggests already that mass really is just a manifestation in the field. It doesn't necessarily have to be the gravitational field, but some kind of field. And well, a natural candidate for this is the soliton. And solitons are long known. They were first observed in hydrodynamics, in channel waves, and later also in plasmas and stuff like that. And it is a nonlinear wave packet which is stable and self-reinforcing. And it can propagate shape preserving over a long time. And even if it collides with other solitons, it retains its original shape after the collision.
Which sounds a lot like a particle.
Exactly.
Yeah. Now let me back up to make sure we're understanding all of this so far. So you've said that inertia, which is a property of matter, the resistance to acceleration, that there's evidence that that is really a result of gravitational interactions. Mm-hmm. And this comes from Mach's principle. Now, I know we're not going to focus today on Mach's principle, but it's a key part of your background argument. So give us a quick understanding of the evidence and reasoning steps that leads us to the idea that inertia is a result of gravitational interactions.
Yes, well, I think the most famous evidence there is really the equivalence principle, which is a postulate. I think many people are not really aware that it is not really a proven result, but it is just measured. It is not explained in current physics. And that inertial mass and gravitational mass are equivalent, or at least proportional to each other. This already is a very strong hint that the inertial mass might have a gravitational origin. Yes, if one explains this in context of these Machian theories, it also comes out. So one can actually derive the equivalence principle instead of having to postulate it.
And yeah,
from that one can also derive a formula for the gravitational constant, and it is then g is something like speed of light squared over 2 times the gravitational potential of the universe, and this is very well confirmed by observations.
Mm-hmm.
So there's also a quantitative evidence for this hypothesis.
I see. So yeah, and putting so my quick way of understanding this is that there's evidence that you can derive the gravitational constant from the mass distribution of the universe. And what does that mean? It means that inertia is really a result of not just the property of individual bodies, but it's the result of some kind of interaction between all bodies with one another.
Exactly.
Yeah.
This is the original idea that Mach had in mind. He didn't necessarily think of the gravitational field, but he said that inertia is not an intrinsic property of a body, but it is a result of an interaction with all other masses in the universe.
Mm-hmm.
And the equivalence principle suggests that this interaction is actually the gravitational field.
Right. Yeah. So we already, and Mach at the time used the bucket experiment as an argument for this, which is the question is why in Newton's bucket, if you haven't heard of this, audience, you need to look this up. So the idea is like when a bucket of water spins and it deforms, why is it deforming? What is it spinning with respect to? And Newton said absolute space. Now, I personally don't agree with that. I would tend to think it's spinning with respect to the ether. Well, Mach says it's spinning with respect to all the other masses in the universe. And so that was his argument. Now, personally, I think it might be both. Like it's spinning with respect to the ether, but part of what conditions the ether toward making that local change is the mass distribution of the universe. And I think Mach didn't have a very, based on what I know right now, Mach wouldn't have been able to really account for that, but the equivalence principle in general relativity is a good argument for that, that the masses influence the ether, and then the ether in turn influences the properties of the matter. And in this case, and part of your hypothesis is that it influences its inertia. Is that accurate?
Yes,
Cool.
yes.
All
And
right.
there
Well, that's yeah.
from the bucket experiment, or going into the same direction of the bucket experiment, there's also another evidence for the correctness of Mach's hypothesis. And it is the measurement of the rotational frequency of the Earth. One can measure it dynamically with the Foucault pendulum, and one can measure it by observing the distant stars. And both measurements agree. And they actually measure two different things, because the dynamical measurement measures the rotation with respect to absolute space in Newton's language. But the measurement of the distant stars, the observation of the distant stars, measures the rotation with respect to all other masses in the universe. And if they agree, this is a remarkable coincidence in the Newtonian framework, because there is no reason to assume that the Earth spins with the same frequency with respect to the stars and with respect to absolute space. But in Mach's hypothesis, this is of course expected, because they are the same. And the dynamical measurement measures the rotational frequency with respect to these stars. So this is another evidence for the correctness of Mach's hypothesis.
Okay. Yeah, this morning, right before talking to you, I was hearing some fairly convincing arguments against Mach's hypothesis. But now these are also some things to consider that I just didn't think of this before. So that's now, because I would tend to think, well, why do we really need Mach's hypothesis? Can't we just say that it's rotating that the Earth is rotating with respect to the ether? And you'd say, yeah, maybe, but then how do you account for the fact that the stars, the distant stars, are all apparently rotationally at rest with respect to the ether? I mean, maybe that's just how it turned out, or maybe the nature of the ether is conditioned by the distribution of masses within it. And because of the nature of gravity, we already know this is true in a certain respect. Gravitational forces, I mean, in my view, I'm convinced of this from the things I gave in my PAMO presentation. Gravitational forces are caused by, and gravitational effects like gravitational time dilation, these are caused by masses influencing the nearby ether. So we already know masses influence the ether, and then the ether influences masses, and you're giving an argument for one additional way that it would do that, in that it affects its inertia.
Yes, and in the if one follows the soliton idea and says that mass is a special manifestation in the field, then you get a different picture of not particles moving through the ether, but the particles actually are part of the ether.
Yeah.
So it's actually not two different things, but you just have one field or ether. It's kind of similar. And so in the soliton picture, the ether really is the field, and the solitons are part of the field. And just the core parts and the far fields are what is usually known as fields, so the gravitational field and the electrical field.
Right. Yeah, so there's like this, and this is something I also gave in my presentation, which is that the Schrödinger equation is already, if you analyze the Schrödinger equation in a certain way, we already know, in my view, for certain, that mass has at least one element of mass is a wave in the ether. And what you're positing is that maybe the whole thing is a wave in the ether. It's not just it's not a the de Broglie-Bohm picture where you have a wave pushing particles around, but maybe it's really, and you're going to get into this, there's a wave, there's like an overarching de Broglie-Bohm wave, and then within that packet, or within that envelope, is a soliton. And the de
Yes.
Broglie wave tells the soliton where I mean, I'm being a little silly there, but like it tells the soliton where to go. It affects the motion of the soliton, but the soliton itself, the particle in quotes, is also just a wave in the ether.
Yes. It's almost like that. It's
Okay.
more like the whole thing is the soliton.
Mm,
So it is really constituted of like two functions, roughly speaking, and it's a product of two functions like f and psi, and the psi is the internal oscillation. It's some oscillating function, and the f is the envelope, which describes it's like the amplitude, and it's a wave packet.
okay, I was misunderstanding that because so F is the F and F is the soliton, is the soliton solution.
The whole thing is the soliton solution. So you
Okay.
have something like U is equals F times psi, and U is the soliton.
Mm-hmm.
And
I
F
see.
is the envelope function, and psi is the internal oscillation.
I see. Okay, so let's before we get deeper into this, a few notes for the audience. I've linked Dennis's paper in the description, so you guys can follow along with some of that for a deeper understanding. And right now, we're looking at equation 1.6 in that paper. So let me now let me get clear on this. So in this hypothesis, the soliton has two parts, F times psi, and psi is the psi we already know about. It's the solution to the Schrodinger equation. What I was understanding is that psi is I took a Bohmian view of this psi, and maybe this isn't the right way to think about your hypothesis. I took a Bohmian view of this psi, that it was like a guiding function, that it's the envelope, and then that kind of determines where F goes. But that's not right. You're saying that F is the envelope, and then psi is the oscillations within that envelope.
Exactly, yes.
I see. Um, okay, I have some questions, but let's let you just continue explaining from here. I think it might come together for me.
This is actually the double solution idea of de Broglie. It's in one of his later works where he said that this psi, which is actually the quantum mechanical wave function, that this alone is incomplete, and that thus also quantum mechanics is incomplete, but that the complete theory has these two parts, like this F and the psi, and together they obey a nonlinear equation. So this U obeys a nonlinear equation, and only this whole thing is the particle, and the psi alone is missing something, namely this F, this amplitude function.
Yeah,
And
and oh,
quantum mechanics is only dealing with the psi function and not with the whole thing.
right. Yeah. Okay. And let me explain what linear versus nonlinear is. With psi, that's a linear solution to a linear differential equation. And what linear means, tell me if there's more to it, but my understanding of linear is that all of the derivatives appear in a single power. They do not appear inside of a nonlinear function, and they only occur in one power. So, for example, in the Schrodinger equation, we have a space derivative. I'm sorry, a second spatial derivative, and it's to the first power. we have a time derivative, and it's to the first power. But what you're proposing is something very is something fairly complicated in my mind, because I don't know how to solve nonlinear differential equations myself. I'm looking at let's see, equation 1.7, and we're seeing there's a linear operator, there's a linear differential operator on one side, but then the wave function is inside of a sine function. So that's a non-linear function of phi, which is your wave function. It's a non-linear. So what we have here in 1.7 is a non-linear differential equation. Right?
Yes, this is one famous example of a nonlinear equation. It's not like the field equation now, but it's just a toy model.
I see. Okay.
One which is very well studied, the Sine-Gordon equation. And yes, this is nonlinear. And
I see.
What is also characteristic for linear differential equations is that you have a superposition principle, so that the sum of two solutions is again a solution. And this doesn't apply anymore for nonlinear equations.
Now, physically, what does that mean? What's the difference physically between linear and nonlinear in terms of the superposition principle?
Physically, this means that solutions don't interact with each other. So if you have in a linear differential equation, since the sum of two solutions is again a solution, they don't interact with each other.
Yeah.
But
so the waves will just pass. They'll just go. Sorry.
In a nonlinear equation, it's different. They interact automatically with each other, and this is also one of the promising parts of it. Because you don't have to put in fields, interaction fields by hand, if you have something like solitons, which are solutions to nonlinear equations, but they automatically interact with each other. And this gives the possibility to actually derive the interactions instead of having to postulate them.
Yeah. You know what's interesting? I've always had a few thoughts on this. So whenever I look at a linear wave equation, say, for something really simple, like a string, just like a literal steel string on a guitar, for example. Those linear equations presume that all deformations of the spring are quite small, right? It presumes that. And I always wondered, well, where is that presumption coming from? Maybe now, here's the thing. For a normally oscillating guitar string, I guess that presumption is close enough to the truth that you don't need to worry about any nonlinearity. And so it ends up working just fine. But when we get into the Schrödinger equation, I've always found the following very interesting. You have to, in the Schrödinger equation, seems like a very clunky way of dealing with interactions between particles, because how are interactions dealt with? They're basically dealt with that potential term. You solve for one particle, say the electron in the hydrogen atom, and what is it that, what is it that determines the behavior of the electron? Well, it's the dynamics of the wave equation itself. It's the which I equate with the nature of the medium. The nature of the medium is what leads to the first time derivative in the Schrödinger equation and the second spatial derivative. But then V, the potential function, is the interaction of the electron with nearby bodies. And I always thought that was a little clunky, because then I asked, well, wait a second, that body is also going to be affected by the electron. Now, in the case of the hydrogen atom, I think you get away with it, because the situation is Keplerian. I'm putting that in quotes, and what I mean by that is sort of a crude way of saying the big thing in the center doesn't get affected that much by the small thing going around it. And so so that's acceptable, but then as a result, but then how is it when two objects actually interact with one another as equal partners? Maybe that's what a soliton solution can provide us.
You can also in the in the two-body problem in quantum mechanics, you can actually do the same trick with you do in classical mechanics, that you go into the center of mass frame, and then you don't have to make this approximation. You can solve it exactly, even if you don't. For something like the positronium atom, where both partners have equal mass, you can still solve it exactly by going into the center of mass frame. And then you get a product wave function. One is for the center of mass, and one is for the actual, for the small radial, for the radial coordinate between the two.
Okay,
So
I didn't know that. That's important to note. So I'm seeing the overarching reasoning here, which is in order to get there's a lot of evidence that there aren't really particles, that really these things are waves. And one way, and the question you and your collaborators have asked is, well, what kind of waves have these kinds of properties? And the answer is solitons. And what kind of field equation leads to solitons? Well, it's a family of nonlinear equations.
Yes.
Yeah, and so this family of nonlinear equations is therefore they're all candidates for the true field equations that the Schrodinger equation just kind of only scratches the surface of. And I mean, not just the Schrodinger equation, but all of these, like the Klein-Gordon equation, and these are linear equations that they're giving us some of the story of what the ether is doing, but not all of it. Then really, the field equations, or maybe we could say the equations that govern the interactions of the parts of the ether, they're actually non-linear. And exactly. That the linear is just an approximation. Because, I think that gives a nice summary. Why don't you keep going?
Yeah, let me leave one comment also, that solitons are an intrinsically nonlinear phenomenon. So you can only have soliton solutions to nonlinear equations. You don't have them to linear equations. So if one follows the soliton approach, one necessarily needs nonlinear equations.
Yeah.
And in this de Broglie picture, where U is the field and it is composed of two parts, the F and the psi, then one can say that the psi obeys the usual quantum mechanical wave equation, which is then the Schrödinger equation, or in the relativistic version, it's the Klein-Gordon equation. And the whole thing obeys the nonlinear field equation, whatever this might be in the end.
Okay, got it. I see. Whatever that might end up being. I see. Okay. Well, I'm satisfied. Keep telling us more about these.
Yeah, one can of course think in what way one might be able to obtain such a nonlinear field equation, and one can apply the conclusion which we draw earlier for the gravitational field, and just write down the simplest relativistic field equation for the gravitational field, which is something like wave operator on U equals 4p times gravitational constant times mass density. And if one then assumes that the mass is part of the gravitational field, then the right-hand side, the 4 pi g times mass density, gets some function of the field. And with this, one has a nonlinear wave equation. And this has, depending on the form of this potential V of U, it has soliton solutions. And of course, these are still not the correct field equations. It's not like that one can yet already describe a proton with it. But one has a Lorentz invariant nonlinear field equation, and which can have soliton solutions. And these already have very interesting properties, like all the relativistic effects, the solitons length contract, and the internal oscillations time dilate, just as a result from the Lorentz invariance of the underlying field equation.
Okay, yeah, okay. This is really cool. So let's break this down. You said you verbally stated some math. We're not showing the actually, I mean, I got your paper here. I can show the audience the math. I think I'm not going to do that at first though. Let's just describe the math in physical terms. So the first thing you did, I'm looking at section 2 of your paper, and what the heck, I'll show the math because it'll help. It'll help, but so I'm going to show Dennis's math here. Okay, let's see. This is it, right? Let's see. Yeah, this is it. Okay, there we go. Okay, so at the top here we have the normal linear gravitational equation. Okay, let's make it a little bigger here. At the top here, this is the normal linear gravitational equation. What does this represent? This, and tell me if you agree. This represents the fact that, and I'm actually gonna explain this more in a video in 2 weeks, by the way, guys. But I'll just tell you my understanding of this now. If you have a mass, that's this row here. If you have a mass, then it will affect the nearby ether with emanations that spread spherically in space, and they spread over time. That's what this is saying, basically. Again, I'm going to explain how we know that in a later video, but that's what. And so this is just a standard field equation. Now, Dennis, do you agree with that view?
Yes, it's mostly the, just as a toy model, it's the simplest relativistic field equation one could write down for the gravitational field. It also comes out from linearized general relativity. One obtains the same equation in the lowest order. Or from another perspective, it's the most simple relativistic generalization of the usual Poisson equation from Newtonian physics.
Yeah. Yeah, this is... Yeah, right. I mean, to me, I didn't realize this was relativistic. This seems Newtonian to me. This just seems like a Newtonian Poisson equation.
It would be Newtonian if you had a Laplacian on the left side, but you have a D'Alembert operator, so the wave operator.
Right. I'm forgetting that the Newtonian picture is basically implicit action at a distance, whereas this isn't. Yeah,
exactly.
Okay,
and
okay.
This has retarded solutions, so it's not actually
exactly right. And retard, by the way, anyone who doesn't know, retarded solutions here doesn't mean solutions that are like stupid or easy to get. It means solution. It means that delayed spreading. It's that not only does the field emanate outward from the mass, but it emanates outward in a think of retarded, think of tardy, like it's late. It takes a while to get out there. It's delayed. That's what the word retarded really means. It means delayed. So, yeah. So, okay. Then now, this part I find very interesting. You say, if we assume mass is now part of the gravitational field, we can write the description in this form. Now, let's first... mass, if we assume mass is part of the gravitational field, tell us more about what you mean by that.
Well, it's basically what we already talked about earlier, that you don't have mass as something separate from the field, but it's what we currently describe as mass is just one I'm currently lacking the English translation.
One manifestation of the field?
Manifestation, exactly, yes. It's one manifestation of the field.
Right. Yeah, so here's my way of thinking about it, and you can correct me if I am going astray here. Is that the ether um, can have more or less of a certain property, and that property causes gravitational forces. But not only does that property of different amounts at different locations, not only does that cause gravitational forces, but it is the very same as the matter. Let me be even more specific here. So Maxwell's model for the ether, the electromagnetic ether, Maxwell's model, he modeled charges as he modeled positive charges as portions of the ether that were dense with electromagnetic substance. He thought the ether was filled with electromagnetic substance. In certain places it's denser, in certain places it's rarer. And he modeled the positive charges as dense chunks of the ether and negative charges as rare means not dense, rare chunks of the ether. And between these bodies of various densities are pressure fields, basically. So you're talking about something like that, but for mass and gravitation.
Yes, there are similarities, yes.
Okay, it's
Because
only similar, it's not the same.
in the usual picture you have just particles with masses, and they are generating fields, and the fields are acting back on the particles. And in the soliton picture, it is really just two parts of the same field. So you have something like the core field and the far field, and it's just two parts of the field, and the core field is the particle, and the far field is what is usually termed as field. But they are not separated, but it is just one field which describes both.
I see. So right there, you're giving a more general description of this perspective we should probably have while thinking about the ether. Whereas what I was giving an example of this same kind of, a concrete example of how to think of it this way. But you're saying, I don't necessarily think of it exactly the same way Maxwell did, but I'm taking that same general approach where the source of these forces really has the same underlying substance and form of as the causes of those forces. The mass and the gravitation are really expressions of the same property of the ether.
Yes,
Yeah.
exactly.
Yeah,
And,
that's
and
very
when I talk about field, it's the same that you are talking about when you say ether. So it's really just two different, in my view, it's just two different words for basically the same thing.
I disagree with that, but I'm not going to bother you about that right now. I'm more interested in everything else you have to say. So we'll table that as a discussion for later. So yeah, okay. Well, so carry on. So the next, getting us back on track here. Getting us back on track. You now propose a nonlinear equation here where we, as you said, presume that the field, let's see, the same as is part of the same, that the mass is part of the same thing as the gravitational field. And so we have a linear operator of the field is equal to some nonlinear function of the field. That's what's going on here. And so we get a nonlinear differential equation, right?
Yes, exactly.
And you say the field potential is some function of the gravitational field, and you're not presuming to know what this is yet, right? This is the thing you're not presuming to know yet.
It is just a toy example how one can arrive using this idea that mass is part of the gravitational field, how one can arrive at a nonlinear equation which has soliton solutions. And depending on the form of this V, soliton solutions of this equation have already been found, and they are also in the literature in 1 dimension and in 3 dimensions. This Sine-Gordon equation we mentioned earlier is of this form. And one also has other equations of this form in 3 dimensions, which have soliton solutions.
Right. By the way, for everyone's information, this is the Sine-Gordon equation here. So once again, a non-linear differential equation. And once again, to tie this all back to the evidence, why are we talking about these non-linear equations again? The reason is because the solitons are the solutions to nonlinear equations, and there's a lot of evidence that these so-called particles that we experience, these small particles we experience, are really solitons. They're a certain kind of wave that arises from a nonlinear, different families of nonlinear interactions of the parts of a medium.
Yes, it was so that the solitons were observed in mostly in hydrodynamics or in plasma physics, in channels or on the ocean, and one found these objects there, and one observed that they behave like particles in experiments on the one side and mathematically on the other side. And yes, it is an observation that they behave like particles, that they have these properties. And it is kind of remarkable because initially one has found these objects in fields and areas which had nothing to do with particle physics. And one was really surprised to see that they actually behave like particles. Solid bodies is also a field, crystal dislocations and something like that, where one have solitons. So there they were first observed.
Yeah, that's very remarkable, and it's nice because we have solutions to a lot of these hydrodynamic and plasma solitons. We actually we understand the math behind them, right? Yeah. So that's a really good lead. Now, you said earlier that these solutions are Lorentz invariant, is what you were telling me. And this is another very alluring aspect of this approach. So tell us more about that.
Yes. First of all, not all solitons are just Lorentz invariant. There are also something like the Korteweg-de Vries equation, also most of the hydrodynamic equation. They are, of course, not Lorentz invariant because the underlying field equations are not. But if one constructs solitons from something like a nonlinear wave equation, which is Lorentz invariant, then the solitons inherit this Lorentz invariance. They are also. And this leads to the soliton solutions showing the known effects like length contraction, or if they have an internal oscillation like this de Broglie waves, then the internal oscillation also is dilated. So if the soliton moves, the internal oscillation goes slower by just the same Lorentz factor as one knows from the time dilation formula. And the soliton is length contracted, this envelope function is length contracted into the direction of motion by the same known Lorentz factor as one knows from special relativity, but not perpendicular to the direction of motion.
And that falls just directly out of the math for many solutions to some of the possible field equations.
Yeah, it's actually for all solitons which are solutions to Lorentz invariant field equations. One gets these properties.
Right.
Yes.
Right. Yeah. Now, okay. This might be getting a little too deep into the math. We can skip this if you'd like. But what exactly does it mean for the field equation to be Lorentz invariant? I kind of know what that means, but tell us in detail if you can.
Yeah, it's basically the same as with Maxwell's equations. If you Lorentz transform Maxwell's equations into a moving frame, then and express them in the primed coordinates x dash and t dash, then they have the same form. They stay invariant. So whether you express them in x dash and t dash or in x and t, they look the same. And this is what Lorentz invariant means. And every field equation which has this property is Lorentz invariant. And one can simply check for for example, all the nonlinear wave equations, they are all Lorentz invariant because you have the wave operator on the left side, and this is, of course, a Lorentz invariant, as we know from Maxwell's equations. And on the right side, there's no differential operator. There's just some function of the field, and this is not affected under Lorentz transformations. And so all nonlinear wave equations, which have something like wave operator on U equals nonlinearity of U, are Lorentz invariant.
They all do.
Yes.
Huh. Wow. You wouldn't think that. I'm not sure what to do with that information, but that's kind of surprising that they all do. It's kind of a shame that they all do, because if only a very narrow class of these equations were Lorentz invariant, that would narrow down what the field equations would have to be, right? Because we know that they're gonna exhibit these properties. So, but let's actually return to the really remarkable thing here. If this dynamics that already has some evidence for it, because these fundamental particles behave a lot like solitons, this dynamics automatically produces waves that shrink as they move through the ether, length contraction, and their internal oscillations get longer as they move through the ether, and that is time dilation. Only it's, by the way, it's not length contraction and time dilation as it appears in special relativity. It is these phenomena as they appear in a Lorentz ether theory, where everything is in reference to the rest frame of an ether. It's not that things are relative. It's I don't even want to use the word relativity in relation to this, because it's not relative in this view. It's relative to the ether.
Yes.
Exactly. So that's that's a very strong feature of this. That's one of the things that really had me excited about your presentation. So tell us more. What other features does this soliton model have?
Yeah, just another addition to the length contraction and time dilation stuff. It's the way the effects work there is actually different from special relativity. Not only that they occur with when something moves relative to the rest frame of the field or the ether, but also how they work. Because in special relativity, or also in the Lorentzian ether theory, it's actually really time dilating and space contracting. While in the soliton model, it is not. There, it is the matter is changing. So space and time are not affected. They are just the background, passive background, which is not interacting at all with the matter. But since the solitons contract and the internal oscillations dilate, your rulers and clocks, which are the solitons or build of the solitons, they change. And this is the way that length contraction and time dilation occur as measurement effects from your rulers and clocks changing, and it is not space and time changing.
Right. I mean, that on its own is, in my view, I've always thought the idea that space itself changes in different frames, or time itself changes in different, I've always considered that to just be a metaphysical corruption.
Yes. Exactly.
And so you can see, and so this hypothesis is in line with a proper metaphysics of time and space, that time and space are these relationships, and that when you change and by the way, this is why I call it duration dilation, because when you call it time dilation, it's not, you don't have to think of it this way, but it lends itself towards this this view of, you know, time being this disembodied dimension that can be squished, but it isn't. It's just a measurement of changes. And if your process that you're using as your measure of change, if that process changes, then you'll measure time differently. It's not that time
Exactly.
changed. Yeah, it's that the
Yes.
duration changed. Now, either the duration you are measuring changed as a result of its motion through the ether, or your the duration of your clock tick changed as a result of its movement through the ether, or both. And usually it's both, and that's what makes it's one of the things that makes this so complicated.
Yeah, and the in the soliton model, it is basically something like clock dilation. So it's just the clock really running slower,
Yeah.
and your ruler gets contracted, but space and time, they are unaffected.
Yeah.
Of course, if you measure a duration, like you say, then you have a change because you're using a different clock. Or if another clock moves through the field or through the ether, then its internal oscillation is also slower, but not because time is running slower, but just because of the mentioned effect that this internal oscillation of the soliton is slowed down when it moves relative to the ether. And yeah, so also the Lorentz transformations, they are then measurement effects. And the same also applies to the constancy of the speed of light. So the speed of light is not actually constant in a soliton model, but it behaves the usual vector addition. But it appears constant because when you measure it from a moving frame, you have different rulers and different clocks. They are dilated and contracted. And if you then measure the speed of light and do the calculations, everything crosses out and you get C again. So
Yeah.
it is apparently constant.
Yeah. Let's add another detail to this that I noticed, and you can tell me if I'm understanding this properly. When you say the constancy of the speed of light, you mean the constancy of the two-way speed of light.
Yes.
Obviously,
Yeah.
we haven't measured the one-way speed, so we don't know if that's constant, and it probably isn't, right? And under this hypothesis, it would not be, but we can't measure it one way or another. We can't measure it.
Yes.
But what you're saying, so my understanding of what you're saying is, if light is moving with respect at some constant speed with respect to the ether, then the two-way speed of light shouldn't be the same, normally speaking. Because if you do the math, you'll see this. It doesn't cancel out perfectly. You'll get a different two-way speed of light if for example, there's a different two-way speed of sound if you're moving at different speeds with respect to the air. So why isn't that the case for light? Well, your explanation is that the solitons length contract and time dilate in such a way as to cancel that difference, and it falls directly out of the math, and we obtain a constant two-way speed of light no matter how fast you're traveling with respect to the ether.
Exactly. And
Okay.
if the rulers and the clocks wouldn't change, then one would observe a different speed of light in a moving frame than in the resting frame, similar as to, or exactly the same as for sound. But since they do contract and dilate, the measured speed of light stays the same because the effects cancel out and you get the constancy of the speed of light. And this is actually also an advantage which the soliton model has over special relativity, because special relativity has to postulate the constancy of the speed of light, while the soliton model can derive it. So you don't have to postulate it, but you can show that the speed of light appears the same in all moving frames.
Yeah, and in my way of thinking about this, that's an advantage because you're not simply saying it is, you're saying it is as a result of the inner nature of the ether in this case, and it's always
Exactly.
better to identify more causes.
Yes.
And that's one of the things that really brought us together at PAMO is, I think, modern physics, it's anywhere from ambivalent to it's either ambivalent about identifying causes or it's like neutral about it. It's just like, finding causes doesn't really matter. We just want to make predictions, and it doesn't matter what you see as a postulate, what it is you explain. Just can we get predictions? That's all that matters.
And of course this is a bit of like fooling yourself, because the more you postulate, the easier you can descriptions which match the observations. So you can basically make a theory always fit if you just postulate enough and introduce enough unexplained numbers, free parameters.
Yeah.
If you have at latest at that point where you have more free parameters than you have independent observations, you can make the theory always fit. And so this is a bit of like gaslighting yourself into believing that you are on the right track. And you should aim to reduce the number of postulates and free parameters as much as you can.
Yeah. In order to identify true causes. This is a little bit of a diversion, but here's something to think about. You can comment on this if you want, or we can move past it. LLMs are the introduction of bazillions of free parameters. Just unimaginable legions upon legions of free parameters. Okay, but they're working with, that's different because they're working with a lot of data. It's not like they have a small amount of data and then bazillions of free parameters. They have a ton of data and they're fitting it with a ton of free parameters, basically. So it's not really the same.
What exactly was that? I didn't get the first. What were you talking about? The name of this?
LLMs, so like large language models like ChatGPT, Claude, stuff like this. The way they do this is with tons and tons of free parameters. And I was about to say, like, yeah, I'm totally with you here, but it's interesting that a system with bazillions of free parameters is very successful in certain regards. Yeah.
I think one has to distinguish between something which has to basically work in an applied area, like maybe also an autopilot in an aircraft or something like that, or if you are dealing with fundamental physics or chemistry, or just the fundamentals of the sciences. And I think this is two different things. In application, it is okay if you just describe things. But in fundamental physics, you want to understand things. Or not just in physics, but in all sciences. In the fundamentals and the basics, you want to understand how the things work. And there's not just enough to describe them with thousands of parameters. So this depends a bit on the area you're working in.
Now, soon on Inductica, we're going to be we're actually going to be talking about how just describing things, even for an application, is not as good as some applied system that truly accounts for the identity of something. So the best kind of applications really do follow from a knowledge of causes and a knowledge of identities. But we'll discuss that later on this show. So, but I think, there's a philosophic commitment you and I share, which is a commitment to the identification of the real identities of things, and that's
of course.
And not just description through bazillions of parameters.
Yes, and of course you can always get, also in the applications, you can often get simpler and more efficient descriptions if you understand how the things work and reduce the number of parameters. So, but if you say it just has to work in some way, then of course you can say it's irrelevant how many parameters there are. And I think this is what the physicists basically do in many places. They just say it has to work in some way. It just has to match the observations, and it is irrelevant how messy it becomes.
Yeah.
This is, I think, a part of the problem.
Yeah. And I wonder, Especially when you ask it anything difficult, ChatGPT makes a lot of mistakes. And if you go outside, so it goes to show that, yeah, sure, it might work in a narrow range of cases, but it won't work in the broadest range of cases without knowledge of the things themselves.
Yes, you have to ask it really. You have to put in very much effort into your question, and the better you formulate your question, the better the answer is you get from it. But it's actually really fantastic to quickly acquire knowledge also from different areas of physics when you hear something like for the first time, and you can just ask it, and it puts up very good explanations, and oftentimes they are better understandable than when you directly read it from physics papers, because ChatGPT is, I think, better at explaining. But you
Yeah.
always have to double check it, of course. You cannot just believe what ChatGPT says, because, as you said, it does make mistakes, and you have to check them.
Yeah. I use it every day, and yeah, I basically don't trust it at all. It's just, it offers me some explanation, and then if I fully understand it from first principles, from the things I personally understand, then that's worth something. It gives me
Exactly.
suggestions, basically.
Yes,
Suggestions
exactly.
I'd never be able to think of myself, but just suggestions.
Exactly.
So should we move on to how this model explains quantum phenomena, or are there other things you wanted to talk about for relativistic phenomena?
I think we can move on with just one final remark for the twin paradox. It also doesn't occur in the soliton model. It is removed the same way as it is removed in the ether theories, in the Lorentzian ether theory. It doesn't occur in the first place because the time dilation effects only occur for the one who is moving relative to the ether frame or to the field frame. And so you don't have this paradox that both clocks run slower than the other, but it is only the one which is moving relative to the ether frame. That one runs slower and the other one doesn't. So this is the same as in Lorentz's ether model.
Tying a lot of stuff together. So what about quantum phenomena?
Yeah, one of the basic principles of quantum mechanics we already saw that it is just trivially fulfilled by solitons, which is the wave-particle duality. Because a soliton is a wave, it is a localized wave, and so it diffracts, it scatters, and on the other side it behaves like a particle. This is the special property of solitons, and you have this wave-particle duality, it comes out by itself. And then there is a fairly unknown theorem, which is the bandwidth theorem, which is basically the Heisenberg uncertainty principle, which is valid for all wave packets, so also for solitons. And so as a result of this bandwidth theorem, you just get Heisenberg's uncertainty principle also on its own. It is fulfilled by solitons, or by every wave packet. The soliton is a wave packet, so it also obeys the bandwidth theorem. Physically, you can understand it because the soliton is a spread out distribution, so it doesn't have a singular point in space where the particle actually is, but it is spread around this point, and this leads to uncertainty in the position of the soliton, and the same also applies to the momentum, or also in the time and energy variables. They are spread out. They don't have a singular value, but they are spread out around these points.
Yeah, that makes sense to me. I have a question though for this, and you may want to explain more of this in order to answer this question. So the Schrödinger equation, that leads to a probability distribution of detection events, okay? that's what the solution means. That's all we know for sure that it means. We know with certainty that that solution does mean something, but all it means is that it's the probability of detection events. Now, what is a detection event under this hypothesis? Why is it that even though the wave is spread out, the detection event occurs at only one location? And why is the outcome of that detection event, the location of it, why is it random under this hypothesis?
Well, in the Soliton model, you don't have any randomness, but the wave is just an actual physical wave, and you don't have any probability. It's not a statistical wave like in the quantum mechanics, but it's a physical wave, like.
Okay,
like
so you're saying so it's in the Soliton model, the randomness we experience is epistemological randomness as a result of only knowing psi and not knowing the F part.
Yeah, one could phrase it that way.
Okay, it looks like you want to phrase it a different way.
If you look, for example, at the double slit experiment, you have one has observed that an electron, for example, can interfere with itself when it runs through the double slit. This was is not understandable with point particles, and one has introduced this probability wave in order to explain why an electron interferes with itself, and it produces this interference patterns on the screen behind the double slit. But if you describe particles as waves, they diffract automatically, so you don't need this auxiliary hypothesis of them being some probability waves or so, but the diffraction is just caused by the wave nature, in the same way as you would expect from a water wave, because waves diffract.
That makes perfect sense. Here's what I'm not understanding, though. When we do the double slit experiment, we only get interactions at single locations on the screen at any one time. It really looks like a particle. The particle perspective is not stupid. It comes from direct observation. The real question is, how can an all-wave hypothesis account for these particle-like interactions? So I'm wondering, how is it that the Soliton model accounts for these dots appearing one at a time on the screen, and how does it account for their random appearance?
Yes, because the solitons still have something like a core field and a far field, and the core field is on the same of the same size as the particles are. So if you go far away from it, it looks like a point, but of course it is not an actual point. And the far fields are what is currently termed as fields. And so if this thing hits on a screen, it still looks like a particle if it hits on there due to the core field of the soliton.
I see.
So it still has this particle-like core that just it is not a point, but it is still spread out. It is a spread out distribution.
So the solution to these soliton, the solutions to these nonlinear equations that you are entertaining have they really do have they have two parts to it, a thick part and then a rarer part on the outside that guides the motion of the thick part or the core field. Is that accurate?
Yes, it's the core part is most likely an exponential, so it's decaying exponentially away from the center of the soliton, and the far fields are um, power laws, like the 1 over r or 1 over r squared, as is known from the electrical fields and gravitational fields. So the exponential part is the core, and it decays rapidly. So it really constitutes something like a center. And if you go to multiple radii of 1 over e radii from this thing, it looks like a point from the outside. But it isn't. So it's just an approximation if you go far away from the center of the solid.
If the core is decaying exponentially, you're saying it's spreading out, right?
Yeah, it is spread out. So it's not a point, but a distribution. And this is decaying exponentially.
But that distribution is really small in comparison to the far field.
Yes, exactly.
And it stays small over time, right?
Yes.
I see. And that's the soliton. That is the soliton part, or is the whole thing the solution to the soliton equation?
The whole thing.
I see.
Yes.
I see. But so in these plasma experiments and hydrodynamic experiments, we actually see these solitons with a core field and a far field?
It depends a bit on what equation you investigate, but you see something like a localized field, which is mostly exponential. But you also have examples where it's a power law. It depends a bit on what type of field equation you are investigating. And on
so the for some media, it has this core and outer field and far field property. For other media, it does not.
Yes.
Okay.
And of course, how the structure for the solitons, which then describe the particles, exactly looks like, this still is an open question, because, as said, we don't have the correct field equations yet. And so a final answer to this has to await until they are found.
Mm-hmm.
But this is what would make the most physical sense, that they have these properties.
Mm-hmm. Now, okay. Now, maybe you've already answered this question, but just to make sure I got the answer, why is it that the interactions appear randomly on the screen?
This is, in the double slit experiment, it is most likely just due to the initial conditions, because you don't exactly know where the center of the soliton is, and then if it is a bit more on the left side, it flies through the one, and correspondingly to the on the other side.
So this sounds to me a lot like a de Broglie-Bohm picture, because if you zoom out enough, you don't notice that that these core fields are waves. They look a lot like particles, and they look like they're being guided by a far field guiding wave, just like de Broglie and Bohm said.
Yes, it's similar to this. Yes.
Now here's a question. The de Broglie-Bohm picture is non-local. The particle moves in a way that depends on the distribution of the field right now across the whole field. So it's not retarded, right? It's instantaneous in the same way that Newton's theory appears instantaneous. By the way, Newton didn't think it was instantaneous. He basically just said, I just haven't figured out the retarded nature of it yet. But until I do, the theory looks instantaneous and non-local, and I don't think that's ultimately what's true. It was just an approximation, basically. So a lot of times people say, like, oh, well, Newton was non-local. No, not really. Because he knew it wasn't really non-local anyway. But the de Broglie-Bohm picture really is non-local. Like the way the particle gets pushed around is based on the full distribution of the wave at all locations. Your hypothesis doesn't have that problem, right?
Mm-hmm. Yeah, it's for the solitons, it's more like the other way around. In the usual definition of what deterministic is, it is non-deterministic. Not because the waves are not real, but because the particles are not points. When one, in the context of quantum mechanics or the Bell inequalities, talks about what deterministic means, one is talking about point particles, which have a definite position and a definite momentum, or occur at a definite point in time. And this is of course not the case for solitons, because they are spread out distributions and they obey an uncertainty relation. So according to this definition, the theory is non-deterministic. It is local, but it is non-deterministic, even though the waves are real, because the particles are not points.
In some broad sense of the word deterministic, I would imagine it is, though, because it just deterministically obeys a wave mechanics, right?
Yes.
Okay.
Yes, it is more like the definition of deterministic is a bit iffy in the context of quantum mechanics and the Bell inequalities, because deterministic, the definition of deterministic, implicitly assumes point particles, and this is the problem.
Yeah. Yeah, I always felt like one example was, the Heisenberg uncertainty relation. I always felt like this was basically propaganda. It's like they're framing facts, but they're framing it in a way that really is trying to convince you of something that isn't true. Because I would, once I understood the Heisenberg uncertainty relation, I just thought, well, this is just a basic fact about the nature of waves. This isn't some deep like voodoo about particles not knowing, what gender they are. It's like it's or just to make a joke out of that, but about not knowing, like not having a definite identity. It's that waves are just like this. Waves just
Yes,
just you can't say these kinds of facts about waves. And that's
yes,
not a very deep fact. That's just a fact about waves. It's
exactly.
not some.
And if you're working with point particles, you just can't use this fact because point particles are not waves. This is where you have, because people at the time were thinking of point particles, they had to introduce all this auxiliary stuff with a probability wave in order to be able to apply this theory. But if you start from waves, you don't have this problem, because as you said, it is not it just falls out of the sky naturally if you are working with waves in the first place, because every wave obeys this uncertainty principle. And yes, then you don't have the problem.
Or really, a better word for it is what you put in here. You call it the bandwidth theorem.
Yes,
It's
exactly.
just a property of waves. It's not an uncertainty principle, Yeah.
Exactly.
Yeah. Okay. Very cool. Now let me make sure I'm understanding the answer to my original question. So I asked, why is it that the interactions appear on the screen randomly? And the answer that I'm gathering from this is that we don't know where the core fields are to begin with, and so we don't know where they end up moving.
Yes. Yes,
Okay.
at least this is the way I think about it currently.
Now is the mechanics of this, does this end up agreeing with the de Broglie-Bohm hypothesis in the macroscopic, or not macroscopic, but in the far field regime, or is it just different?
I am not really sure, because I have never dug into de Broglie-Bohm too much. I know what it is, and I've read about the theory, but I haven't dug into it too much, because I found de Broglie's double solution hypothesis far more appealing than the de Broglie-Bohm theory.
Right.
If I remember correctly, he started from this double solution theory, and the de Broglie-Bohm theory evolved from that. So he ended up there.
Yeah.
And because the soliton math was not known at the time. If de Broglie would have known that there are solitons which have exactly the structure which he postulated, I'm sure he would have gone into this direction. But it was not known at the time. The math was developed in the late 70s and 80s of the last century. And de Broglie's hypothesis was in the 60s. So it was 20 years earlier.
Mm-hmm. Yeah. Well, we have about 20 minutes left, so why don't you tell us in that time we got, why don't you tell us the other main takeaways you'd like us to other main takeaways you'd like us to take from your work here?
Yeah, maybe a few more words to the quantum phenomena. One has also observed tunneling effects with solitons. For example, in numerical simulations, so they show this automatically. Then discrete energy levels can arise in the same way as it does for standing waves. If you have a wave trapped in a potential well, you get standing waves, and they have discrete energy levels. And the same also works for solitons. One can show this mathematically. For example, the simplest example is just a square well, and if you put a soliton in there and solve it, you get the same energy levels as you would obtain from the Klein-Gordon equation. They agree. Of course, for that the whole spectrum of energy levels is the same as in quantum mechanics, it remains to be shown. It is not proven yet, but in principle this can work. And what is also fascinating is that from these internal oscillations of the solitons, you can actually derive a formula for Planck's constant. And this has the same structure as a currently unexplained coincidence, which is that Planck's constant is approximately equal to the mass of the proton times the radius of the proton times the speed of light. This is the same order of magnitude, and it is currently an unexplained coincidence.
Yeah, so let's dig into that, because I had questions on this. So let's show the coincidence that you are talking about here, which is that H bar is on the same order of magnitude. Oh wait, dude, it's H. It's not H bar that's on the same order. Well, yeah, I mean they're all basically on the same order. I plugged all of this in myself, and what I found was that this expression here is about 2/3 the size of H, not of H bar. It's about 2/3 the size of H.
Yes.
So, okay, what I want to know is, why do you think this is a coincidence? Now I've talked to other Machians at the PAMO conference that showed me other coincidences of this kind. And I mean, you probably remember I was talking to, I forgot his name, but you probably remember me talking to him on the subway, where I asked, well, this seems like just jumbling a bunch of numbers together. It seems to me like, there's enough physical constants out there, like the mass of the proton, the radius of the proton. There's enough physical constants out there that if you jumble them up in any way you want, you can end up with any goddamn number you want. So, I think I'm not the only one who's going to be skeptical of assigning this expression any significance whatsoever, especially when it doesn't match exactly. If it matched exactly, maybe I'd say, oh wow, like that does seem pretty wacky, but it doesn't match exactly. So can you give me some argumentation for why we should take this seriously?
Yes, well, first it is really, even though you have quite some physical constants, it's not too likely that if you put them together that you end up with such a coincidence. They are quite rare. So, and I'm not talking about something like, of course you can now raise the constant into the pi third power or something like that. And then if you tinker around with it long enough, then you get a match. But I'm something which appears kind of natural. So like mass of the proton times radius of the proton times speed of light,
Just a
or that
simple
the gravitational
multiplication.
constant. Yeah,
It's just a simple multiplication.
yes. Or like the coincidence which was investigated by Schrödinger 100 years ago, that is g is of the same order of magnitude as the speed of light divided by the gravitational potential of the universe. Those are simple relations. By the way, that c is 1 over square root of mu naught times epsilon naught. It was also found in the same way because Weber did dimensional analysis and found that mu naught and epsilon naught have the same dimension as a velocity squared to the -1, and that they are of the same order of magnitude as the speed of light. And so he hypothesized that it might be true, and only later were it confirmed by even more precise measurements. So if you
Okay,
get
okay.
simple relations, not something crazy like with 5/3 power or like that, then there is a very high likelihood that there is a meaning to it.
Okay.
And so this is the first thing, and then that it is only of order of magnitude, but not exactly. This can very well be understood or in the case of the gravitational constant and in the case of the of Planck's constant, because for the gravitational constant, it is on the one hand side the uncertainties in the measurement of the mass of the universe and the radius of the universe,
Yeah.
and of course the exact factor in front is not known. So some theories say it is 4, some say it is 2. It depends a bit on what theory you build. And which factor it is exactly will only be known once either the measurements of the mass and the radius of the universe are precise enough to pin down one factor, or the correct theory is known and one knows for certain that must be like a factor of 2 or a factor of 4.
So
And
that sounds, yeah. That sounds really good, but it seems to me like you're in trouble here. Because as far as I know, all of these are very well understood values. So you don't are very well measured values. So you don't have any wiggle room there. When it comes to, what was it, the gravitational potential of the universe, we could absolutely be off, right? We could absolutely be off, and the fact that we get order of magnitude agreement has some weight because it's within the bounds of uncertainty. But there are no bounds of uncertainty on these values, right? I mean, I'm not well acquainted with how they were measured, but I would imagine they are well measured, aren't they?
yes, but it here comes from the definition of the radius. Because in a soliton model, you don't have a fixed radius for a particle, but it is something like a 1 over e radius. And depending on the theory, you also get a prefactor in front of it. So it can be something like 5/3 or 7/2 or something like that, something of the order of magnitude of 1. And this radius is something like a 1 over e radius. And it is not a precise value.
It's not
And
a
so
real
depending on the
radius.
theory,
It's
yeah.
not really a radius.
Yes,
Yeah.
yes. It's more like 1 over e radius, something like you have in a disk galaxy or in a bulge galaxy. They don't have a fixed radius because they don't end at a certain point, but you have a 1 over e radius where the density has fallen to 1 over e of the value it has at the center. And something like that you can define. And of course, it then depends on the definition, the exact definition which you choose for this radius. And this varies from one soliton model to the other. So depending on what field equation you have, there is a wiggle room for a prefactor of the order of magnitude 1. And so this is where this comes from. So for example, in the Sine-Gordon theory, you have something like I think 1 over cosine of q or something like that sitting in front. And depending on what you put in for q, you have maybe a factor of square root of 2 or square root of 3 or something like that sitting in front of it. And it depends on the concrete model. So you can only really talk about the order of magnitude in this formula. But of course, if the correct field equations are found, then with the factor you get in this theory, it is expected to match exactly, of course. Yes.
I see. Okay. Let's see. What else? What other features did you want to tell us about this theory before we go?
Yeah, maybe another point is that you don't have to apply something like renormalization, because the infinite self-energies only occur when you work with point particles. But since solitons are spread out distributions, they have a regular energy density everywhere. And you don't have this problem. They have a well-defined finite energy, and you don't have to deal with infinite masses which you have to subtract.
Right.
So
that's yeah, and you don't. Yeah, basically, when you're integrating over 1 over r, there's certain positions where the value of that function is it blows up. So what does it come out to? And they have these tricks to get around that, but in this model you don't need the tricks, because you're never getting infinitely close to this, this point-like object. Now, yeah, so this resolves that paradox. Tell me about how this model would treat Bell's theorem. I don't know if I really understood this part of the paper, by the way.
Yes, well, a final answer to Bell's theorem will have to wait until it is known how spin and entanglement work in the soliton model. There are some hints that spin might be topological origin, but there is nothing definitely developed until now. So this is
what do you mean spin has a topological origin? What does that mean?
It is similar to what Chantal presented at the PAMO conference, that you have this twists where if you turn it around once, it is entangled, and if you turn it around twice, it is disentangled. Something very similar like that you can construct with topological solitons. And this is something we are working on currently. Topological solitons also have some other very interesting properties, like they automatically have something like a discrete charge, and the interaction between those depends on the value of this charge, and so you get an electromagnetic type interaction between them automatically. And this is also they have some very interesting properties, but it is currently under investigation. It's not like we have a definite answer to that, how spin and entanglement work. It's a promising road, but it's not definite.
Okay. Yep. Sounds good. That's really good to point out the places where you haven't worked it out. I'm going to give my understanding of what topological means in this context. So here's a supplement bottle I take, and the label is facing us, okay? And I'm holding it in a certain way. Now I'm going to turn it around. Okay, so now you can see the label again. So I've turned it around completely. And so it now is oriented the way it was before. But in order to do this, the relationship between it and the rest of my body is different. Why? Because you can see I have to get into this utterly absurd position to make it happen. Okay, but then if I keep rotating it, we're now back to the comfortable position. So when I think of topology, I think of it's not just the nature of the thing rotating, it's the nature of the thing and its relationship to the nearby medium, and that has the same character as this absurd situation I'm showing you now.
Yes.
Is that accurate?
Yes, exactly. This is exactly the same way one would think about it in the context of solitons. And you can think of your arm like the field connecting the two solitons. And then you basically just have the same idea of how this could work in a soliton model.
Cool. Well, I
Yes.
look forward to seeing what you guys come up with there. Have you seen have you seen the paper from Zeilinger that they observe violation of the Bell's inequalities in the case of non-entangled particles? Have you seen this paper?
No, I haven't. It's the
Yeah.
first time I heard about it.
So I don't know why this paper isn't getting more attention. It might be because it's garbage. I haven't read it yet, so I don't know. But I mean, it's a testament to how busy I am that like I haven't read this yet. But to me, it almost seems like this is evidence that the whole entanglement phenomena might be a red herring. Or this paper is just garbage. That's could be true too. Because if you can violate Bell's inequality in non-entangled particles, then it means there's nothing special about entangled particles. Everything's essentially entangled in this sense.
Well, I don't think it will even constitute a problem if Bell's inequalities hold, because it basically shows that the spin is not something like a momentum which is really oriented in space. But it is this classical picture really is not right in this point. But it doesn't have to be. It can be something different than a momentum oriented in space. So I don't see the problem there. Even if
You're
Bell's
saying like spin can have properties that are not just this simple, basically. That it's just
yes,
it's some
yes,
vector property oriented. I mean, yeah, it just might not be that simple, and then that would be
yes,
enough to violate the Bell inequalities. You think?
yes, I think so. Yes, and
Interesting.
the Bell inequalities and the Stern-Gerlach type experiments, they just suggest that spin is not something like a angular momentum vector which is oriented in space. It is something different. But this is well imaginable that it is something different. And so even if they hold, I mean, there's other evidence for entanglement too. If you, for example, the entangled wave function look different than just simple products, and if you do calculations of the atomic orbits, you get different results if you don't have the correctly entangled wave functions than you get when you do it with just a product. And the measurements clearly show that you need the entangled wave function, the Fermi determinant, and not just a simple product. And so this is also indirect evidence that these completely anti-symmetrized wave functions are correct, and it is not a simple product. And so I don't think there's an error there, but it is really just coming down that spin is not a angular momentum oriented in space. It is a different mechanism at work there.
It'd certainly be interesting to understand more about, because spin has always befuddled me, and so what you're saying sounds very plausible. Well, this whole hypothesis you've presented us, it ties a lot of pieces together, and it has good evidence motivating it. And once we start delving into it, we see that there's real evidence that this might be the way to explain what's going on. So I really wish you and your team luck in finding out more about this, and I'm sure I'll have you on the program in the future as you guys start to discover more. Where can people find out more about your research? I've already linked the paper. Where else should they go?
Yes, well, me and Professor Pavel Krupa from the University of Bonn are currently publishing a paper about the Soliton model, uh, and it is currently under review, so it is not published yet. But it is a, a much more complete version than the one I presented at the PAMO conference. And it also has some other interesting aspects that one can get something like a strong force and confinement out of the soliton picture with a linear potential confining the two pieces, the two quark substructures. And once it is published, I can show you the link or give you the link to the journal page where it appears.
Very good.
Yes. Otherwise, also my homepage, but it is still on an even earlier variant, so to say, than the old paper, and I still have to update it with the new stuff. And I was just busy writing the paper, and now that this is done, I'm planning to update the web page.
Okay, well, you can send me that URL if you'd like, but otherwise, I would really encourage everyone to read the paper. That'll be in the description to get more detail on what Dennis has told us today. And so thanks again for coming on, Dennis, and I'm sure I'll have you on in the future, hopefully when that paper is published.
Thank you for inviting me and for letting me join this talk. It was my pleasure.